Hi everyone, I'm Yashish Madhuvanta, a PhD student in the Electrical and Computer Engineering Department at University of Maryland, College Park. I will be presenting our work titled Learning Audio Synthesizer Controls Inspired by Sensorimotor Interactions, and my co-authors are Guillaume Marion and Shiab Sharma. The existence of bidirectional interactions between auditory and motor regions is a well-known and a proven fact in sensory motor learning. Previous studies on the human cortical speech system with ECOG recordings have shown that learning complex sensory motor mappings proceeds simultaneously and in an unsupervised fashion by listening and speaking all at once. During speaking, motor areas control vocal tract movements that generate a speech signal. It has also been proposed that certain motor cortical areas send a parallel internal neural copy of the speech signal to the auditory cortex. This is called the forward prediction signal, and it is compared with the responses induced by the incoming speech. Similarly, during listening to speech, an inverse mapping from the auditory to the motor areas would create a motor representation of the acoustic signals. Based on these studies on the human cortical speech system, a new autoencoder architecture was proposed by Sharma et al., which was called the mirror network. The essence of this biologically motivated algorithm is the bidirectional flow of interactions between the auditory and motor responsive regions, coupled to the constraints imposed simultaneously by the actual motor plant to be controlled. In this work, we use the MirrorNet architecture to learn control parameters of a commercial and a widely available synthesizer in a completely unsupervised fashion. The goal of the mirror network is to learn two neural projections, an inverse mapping from auditory representations to motor parameters, and a forward mapping from the motor parameters to the auditory representations, which is modeled by the decoder. The encoder and decoder are optimized using two loss functions so that the latent space is constrained to converge to the intended control parameters that can drive the chosen motor plant, or DIVA, synthesizer in this case. As shown in figure 1, the encoder loss EC is computed by taking the mean square error between input spectrogram and the output spectrogram from the decoder. The decoder loss ED is computed by taking the mean square error between decoder spectrogram and the output spectrogram from the motor plant. As shown in figure 2, the key reason behind the proposing an autoencoder architecture lies with the importance of the forward path for backpropagating the encoder loss to learn the inverse mapping. So to implement the autoencoder architecture, we came up with a deep neural network model inspired by the multi-layer temporal convolution network. We use 1D or one-dimensional convolutional layers to model both the encoder and decoder, and also use submodules to perform pre and post-processing and also dilated temporal convolutions. So the detailed information on the model implementation can be found in the paper itself and also in the supporting GitHub repository. So unlike a regular autoencoder, the mirror network is trained in two alternating stages in each iteration. The decoder is trained first to minimize the decoder loss for a chosen number of epochs. Then the encoder is trained to minimize the encoder loss for a given number of epochs, and this alternation of training is continued until both losses converge to a minimum. We use auditory spectrograms as the audio representations, which have a logarithmic frequency scale, simply because they provide a unified multi-resolution representation of the spectral and temporal features likely critical in the perception of sound. We used an off-the-shelf commercial audio synthesizer called Diva with the proposed MirrorNet. The goal is to estimate 7 parameters shaded in yellow in Table 1 to a given melody of notes which contain 5 notes and has a fixed duration of 2 seconds. All the Diva parameters used for learning are continuous and normalized to 0-1 range. We conducted 3 types of experiments with the proposed mirror network architecture to see how well the model can learn the parameters to drive the Diva synthesizer in a completely unsupervised fashion. In experiment 1, we used a dataset of 400 melodies, which we call set 1, that has originally been synthesized by Diva itself by randomly changing the 7 parameters to be learned. The availability of the ground truth parameter data allowed us to assess the accuracy of the MirrorNet predictions. We also performed a preliminary statistical test to evaluate the robustness of the MirrorNet in predicting the 7 parameters. Figure A here validates that the predicted and ground truth parameters are significantly closer together than would result from a random set of values. A second test was performed to check how well the predictions of each parameter are compared to a random prediction. For that, we performed the Lebanese statistical test that confirmed that all parameter predictions were significantly better than chance. Figure B shows that the parameter difference distributions for the test set. The distributions also suggest that critical parameters like pitch, the center frequency for the bandpass filter, the filter resonance, and duration are predicted with significant accuracy, whereas volume and envelope attack parameters are predicted with a comparatively lower accuracy. This shows the auditory spectrograms for a sample audio in the test set. Figure A here shows the auditory spectrogram for the input melody, and figure B shows the decoder output from the ground truth parameters, and figure C shows the final output from the decoder, and figure D is the Diva output from the learned control parameters. The input audio sounds like this, and the synthesized audio from Diva by using the estimated control parameters sounds like this. You can also find similar audio samples and also the resulting audio samples for the subsequent experiments in the mentioned GitHub link. The key observations here are that the spectrogram B suggests how well the decoder has learned to generate an identical spectrogram to the one generated with Diva for the exact same parameters. The spectrogram D suggests how well predicted Diva controls are from the encoder to synthesize an identical melody to the input. In experiment 2, we use a trained set of 400 melodies and a test set of 80 melodies, both Diva generated, which we call set 2, and has been synthesized in similar fashion to set 1, except for the fact that they now use all the 10 parameters in table 1. The MirrorNet is still trained to predict 7 parameters as in previous experiment. The goal here is to demonstrate that the MirrorNet can approximate the input melodies even if they have additional sound qualities that are impossible for the restricted 7 Diva parameters to reproduce. Figure A here shows the input melody of notes, and figure B here shows the synthesized melody by the estimated 7 parameters. A fundamental advantage of the MirrorNet is its ability to discover the Diva parameters corresponding to music generated by other sources and synthesizers by finding parameters that allow the Diva output to be as close as possible to the original input. In this experiment, we used 400 5-note piano melodies that are synthesized by a Fender Rhodes digital imitation, which is a different synthesizer from Diva. Figure C shows the input piano melody, and figure D shows that the network can successfully reproduce accurate renditions of the piano music which closely resembles the input piano melody. So in summary, it is important to highlight that the MirrorNet is a biologically motivated algorithm which simulates the unsupervised learning of vocal tract controls by leveraging on the forward and inverse projections observed between auditory and motor cortices. With this work, we showcase the ability of the mirror network to learn control parameters of a given audio synthesizer to synthesize a given input melody of notes in a completely unsupervised fashion. We also demonstrate the power of the mirror network in approximating an input melody of notes with different sound qualities or synthesized by a different synthesizer by only using the available controls in the Diva synthesizer. Currently, we are working on extending the number of parameters used from the Diva synthesizer to capture richer aspects of sounds. We are also working on developing better training algorithms to efficiently train the mirror network. In future, we are hoping to incorporate advanced and richer representations of sound beyond the auditory spectrums. The next goal of the project would be to synthesize continuous musical melodies which can have variable number of notes in a given frame of music. Finally, we are also working on incorporating a vocal tract model to synthesize a given speech utterance by estimating the vocal tract model's parameters. Thank you.